Okay, let's make a start. So for this Unit 3.4 class, we're going to continue on with the exploration into integrals, into antiderivatives, namely on one of the other key things that we can do with it, which is to find the area under a curve. We'll get into it a bit as to why that actually ends up finding the area under the curve. I have a full little explanation here. But to understand what's going on here, we first need to understand some of the basics as to how we could potentially approximate how much area is under a curve. Basically, the approach is to take these shapes that are otherwise challenging to find the area under, like for instance this curve that's bound by the cosine. Right, there's no generic area formula for that. But we do have generic area formulas for rectangles. So rather than trying to find the area under the entire curve and trying to create a formula for that, what we can instead do is break it up into little sections where each of those sections are defined by some length and width of a rectangle. From there, once you have that, you simply find the areas of each of the rectangles using the rectangle area formula and then just add it all up. And that's going to give you an approximation of the area under the curve. As we can see, it's not necessarily great. You can see there's all these gaps involved in there, and there will always be some amount of gaps. If you want to increase the amount of area or the total percentage of area that's covered, you would simply have to use more shapes involved. So for instance, if we have a look at a little sneak peek of this one, I had an example where I had bigger rectangles, and you can see everything shaded in orange there is the parts that are either missed or overestimated. Right, so here's underestimated, 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 overestimated. If you increase the number of rectangles over the same interval, over the same x interval, then what we notice is that the amount of error in there, the area that's missed, is decreased. And what integration will eventually show us is that if you make these rectangles infinitely small, or infinitely small width, then you can do a bit of math magic to do some antiderivative to get your area formula that is perfectly going to grab the area under the curve. But that's for a bit later. For now, we're just going to do some basic version. We're simply just finding the area of each of these rectangles and then adding them up to approximate that area. Okay, so we've got the procedure all written out here. If you have to do this yourself, then yeah, you're going to divide that interval up into however many spaces you need. In this case, it's already given to us in the question itself. So we already know that each of the widths of these rectangles is going to be pi over 6, and there's going to be 3 in total rectangles. So that's going to give us our width value. Also, if you have to do this yourself, one of the things you'll have to do is decide whether you align the right-hand side or the left-hand side of the rectangles with the curve. That'll be told to you in the question if it requires a certain version. What I mean by that is this would be considered right endpoint aligned. So basically you see you got the rectangle here, the right endpoint of that rectangle is aligned with the curve. The right endpoint of that rectangle, the right endpoint of that rectangle. Left endpoint would be as if I had my rectangle here. All right, I've got the left endpoint. I put another rectangle here. I've got the left endpoint. Final rectangle here. I've got the left endpoint. Depending on which method you use, you'll get either an overestimation or an underestimation of the area. Again, your textbook will tell you which one to use if it's required. In this case, the rectangles, again, already given to us, so we don't have to worry about that for this one. So we already have the width of each of these rectangles. We also need the length, or I guess in this case the height, since it's vertically drawn. The height of each of them, since they exist on the curve, they always plateau and intersect the curve at a particular point. All we're doing is substituting in the relevant x value into that function, since they do intersect the function. So for instance, to get the height here, we're going to sub in pi over 6 into the function. To get the height here, we're going to sub in pi over 3 into the function, so on and so forth. You simplify all of that using your unit circle or otherwise if you remember your CAS, and then you get all of those heights for each of those. We have our heights, we have our widths. Well, area of a rectangle is just height multiplied by width, or length multiplied by width, however you want to write it, just your two dimensions. Multiply them all through, and then finally add them all up. That's going to give you your total area under the curve, or at least the approximate area under the curve, which in this case you would consider to be an underestimation of the total area, simply based on the fact that not all of that area is shaded. We still have some bits left over. That's pretty much all it is. Any questions about how we do any of that so far? Cool. We'll have a very similar example show up again, which is that rectangles are not necessarily the only shapes that you can use. The other type of shape you can use is the trapezoid, and what we'll find pretty quickly is that trapezoids are a far more efficient shape to use because, well, as you can see here, the amount of area that's wasted or that's unrepresented is quite minimal compared to what we saw earlier. The procedure is literally the exact same thing, except for the fact that you're dealing with the trapezium area formula rather than the rectangle area formula. But the things you're doing to get there are the same. Right, you still want to figure out what is the width of all of my shapes because that still matters for the area formula of the trapezium. So in this case, we're not explicitly told what it is, but we do know we've got a total of 4 trapeziums in the interval of -1 to 1. Divide that all up, and we're going to have a half for all of those widths. Again, if you have to do this yourself, you align all of those endpoints up. The good news with the trapezium method is that there's no left or right endpoint to do. Both of them are aligned, right? This is the left of that one, the right of that one, the left of that one, the right of that one. They're all used, and there's no also correct way of doing it. Only one way. From there, again, get the heights using the exact same method. So subbing in x equals -1 into whatever the function is to get the height here. Shoving in x equals -1/2 into the function to get the height there. So on and so forth. Rack them all up, and you have your heights, you have your widths. Just make sure that you're putting that into the trapezium area formula this time. So that's going to be, do I have the generic version? There. So we're basically doing this on its side, where the h value is now like the width. It's like the base of our trapezium. The a and the b are just different heights, right? Because they start at 0, the base of the trapezium, and they go up to however high they exist on the function. So a and b are the heights. A, b for heights, h for the width. And so ordering is exactly that. What you'll notice when you're adding all these areas up is because those points are shared, like for instance, we got our first trapezium here, this endpoint of the first trapezium is the same as the endpoint for the second trapezium. They share the points. So don't feel like you're going this one, this one, this one, this one, and then this one and nothing. You do end up doing a bit of an overlap where you do this height and this height for trapezium 1, then this height and this height for trapezium 2. You double up on all the ones in the middle. If the curve is symmetrical, you can greatly reduce the amount of effort that you put into it. Like if you already know ahead of time, oh shit, this is the same thing, copy pasted left to right. Well, all I'm going to do is do my left-hand side one and then double that up. Because as we can see here, all the heights were the same, all the areas were symmetrical. And that can just save you a little bit of time if you're doing it under test conditions. We'll get into a bit about what I'm talking about here later. Any questions about how this one works? Cool. So what am I going to go on about here? Well, you actually have a formula sheet for the trapezoidal method specifically. I'm going to pull that one up now. And you might look at it immediately and be like, okay, what the hell does any of this stuff mean? Right, I've got a whole bunch of f's in there and some x values. What we're essentially doing is rearranging and redescribing this sequence here of adding up a bunch of trapeziums. So if we think about the area formula of the one we just did, it was basically area 1, area 2, area 3, area 4 all added up together. They had certain width values and they had certain height values associated with it. One of the things that we can see is common across the board is h, right? That h, or the width, is common to literally all of these. Same thing with this division of 2. Those are common factors. So we can take all of that out, leaving you with just the string of coefficients a's and b's. The other thing that we can do to simplify this a bit further is to note again that the trapeziums are back to back. So if this is A1 and B1, this is A2 and B2. Or in other words, B1 is the same as A2. So A1, B1, A2, B2. All I'm trying to get at is the terms are described as different things, but they're actually the same. So what you can do is, instead of having A's and B's, you can actually simplify those into pretty much just A's. Right? There's an A equivalent for each of those. What we'll notice is everything in the middle gets duplicated, like we mentioned earlier. Right? They get doubled up, and the two that are left on the outskirts are kind of left alone. So all of this gets condensed down into a couple of coefficients with 2 in them. Lastly, these A values are just f of x values. More specifically, they are the f of x1, f of x2, whatever those x coordinates are. So rather than writing A for those things, we have f for those things. The height, or the width rather, was a half for each of them, so you could put that there. And that is essentially what is being described here. We can see we've got the f of x values. We can see they're all doubled on the inside. And the only thing that's a bit different is this leading coefficient bit here. So xn and x0 are just the final and first x values. So x0 is going to be the absolute first one. So in our example, x0 would have been -1. It's the first in the sequence. xn is the last x value, which in this case is going to be 1. Everything in the middle, so you've got x0, x1, x2, x3, and finally x4. Lastly, this n here is just a number of shapes that you're using, which in this case is 4. What you'll find is that if you shove in 4 here, 4 here, 4 here, 1 here, and -1 here, that will end up simplifying out to be the same coefficient as this one, 1/4. So I say that because that is on your formula sheet. It is nice to know how that actually works so that you can end up actually using it. But you do also know the fundamentals of how this actually works now. So if worse comes to worse and you have a look at this and you're like, shit, I don't know what's going on there, I'm kind of drawing a blank, you now know at the very least that all we're really doing is adding up shapes under the area that you're trying to evaluate. Any questions about any of that? Going to get onto some practice now. I'm pretty sure this textbook actually, oddly enough, only goes through the trapezium method one, which is good because that's what the exam now does. It's a relatively new addition to the study design, actually. When I was in school, trapezium method wasn't actually taught. It was just the rectangle method. Now they've introduced trapezium, and basically they've still put in the rectangles into the textbook, but it doesn't really show up a whole lot. Like this example that I pulled was from an old exam. Could have even been my exam, actually. Anyway, let's take a stab at it. So 11a, actually what I'll do is, if you want to use the area formula, I'll do a screen grab of that, and I'll put that in the chat. Otherwise, we'll just add up the the shapes, which in this case would be all the trapeziums. Okay, question 1. Find the sum of all of these trapeziums, 0 to 4 of this curve. Get the notes out. In the meantime, have a think about how we're going to do it. Again, either using that formula or adding up all the trapeziums. I've got our function written down as well, and we're doing it from 0 to 4. I've also got the generic area formula for the trapezium up there, if you would like. And what all those terms are referring to when it comes to the trapezium. Any takers? Well, let's start with the widths of these trapeziums. The width is the easiest thing by far to find because it's consistent across all of them. What is the width of each of these trapeziums? 1. Yeah, absolutely 1. Right, so we have a spacing of 1 between them all, so in this case our h is going to be equal to 1. The a and the b values are going to basically be the heights of each of those trapeziums. So we've got a nice little handy guide actually. We don't even have to sub them into the function just yet because we already are given the y values. So for instance, for trapezium 1, we've got a height of 0 and a height of 5. Those are going to be our a and b values for trapezium 1. So we have a1, 0 is the first height, 5 is the second height. The other values, well, height is 1, so we can kind of just ignore it. Gives us 5/2 for the first area of that trapezium. Then we just go on to the next one. All right. Next one is a trapezium between 1 and 2, which has heights of 5 and 14. A2, 5, 14, times 1, 19 on 2. So on and so forth. If we didn't have those labeled, what we would instead do, like let's say we didn't have the heights labeled, what we would instead have to do is substitute in the x values into our function. So for instance, for this area 1, we had the x values of 0 and 1 that were binding the shape that we had. So in other words, we're trying to find f of 0 and f of 1, which is our function, right? Because we're trying to find the area under this function. The curve is bound, the trapeziums are bound by that curve. F of 0, clearly just going to be 0 if you put zeros in those x's, which is why we had a 0 for that first one. F of 1 is just going to be 2 plus 3 for 5, which again we have here. So if you have to do that, this is the way to do it. Otherwise, if you can just read them directly off the graph, then by all means, read them directly off the graph. Let's just finish them up. A3, so that's going to be the 14 and a 27. 14, 27, and A4, that was 27 and 44. 27, 44. Alright, so 44 over 2, which is 22. That doesn't seem right. 41 over 2. And actually, same thing here, pretty much. 4, 6, 7. That's for our total area, which is going to be the sum of the A1, A2, A3, A4. All we're doing is addition here now. 5, 19, 41, 71, all over 2. I'm just going to cast that out. 71, 41, 19, 5, 136 over 2, which comes out to be 68. Do they give anything for units? No. So we're fine to just leave that as 68. If you want, maybe you can do something like units squared. But every answer in the textbook, pretty sure doesn't. Let me just double check that actually. We've seen it a couple of times where basically it won't. Yeah, it's just the answer, 68, nothing else. Explain the first part of the formula, yes. So this first part here, xn and x0, if you remember from maybe Newton's method, xn, x0, those subscripts just tell you what x value in the sequence that you're referring to, where all sequences start at 0 by convention. So in this case, x0 would be 0, x1 would be 1, x2 would be 2, 3, 4, so on and so forth. So that shows you how to use those. Same thing with the bits in the middle, actually, x0, x1, x2. These n-2, n-1s, n is just the final one in the sequence, which is why they have to write it that way, because the sequence could be arbitrarily long. It's basically all you've got to think about is the x0 is the very beginning, and then every single one after that is the next x value. Last thing is just the n. That's just the number of shapes that you're using. So in this case, we did 1, 2, 3, 4, so n would be 4. So if we use that method, let's take a stab at that. So xn minus x0, that's going to be 4 minus 0. So 4 take 0, 2 times n. N was 4 because we had 4 shapes. Then from there, so that was the f of x0, f of x1, 2, 3, and so on. So f of x0, that's just the y value at the very beginning, which of course is 0. Then it's 2 times everything in the middle. So we know the next one was 5. We know the next one after that was 14. And the next one after that is 27. And since 44 is at the very end, that does not get the coefficient of 2. Just stays as is. 4s are going to cancel down, leaving with half. That's not how, yeah, 4's are 8. And then, so that's going to get us 10, 14, 28, 27, 14, 4, and 44, which are all the same. Or at least that's what you would get from all of those. I'll just quickly cas that all out. 10, 28, 54, 44 gets us again 136, and then we're finally dividing that by 2 because of that coefficient over half. 6 divided by 2, once again gets us to 68. So that's the formula sheet version. So adding up the areas themselves is probably a bit more intuitive because we've done areas basically for our entire math career. this one might take a bit of understanding for the notation of how it all works, but is technically faster. If we have a look at like the sheer amount of space that it covers, we did all of this for that answer, and we did all of this for this answer. Now, granted, you're just doing a lot more mental math in the middle here than you are for here, because you're kind of separating out into stages, but yeah, it's ever so slightly more efficient to do it this way. Any questions about that? Because these questions are going to play out the exact same way every single time. You just look at the curve, get your y values off of that, plug it into area formula. Do we need to practice any more of those? Or shall we move on to the integral?
Would we be able to do one more quickly?
Yeah, certainly. So we'll do question 2 here, just because it's going to force us to actually use the function that's bound. Because yes, we do have some axes labels here, but if you look at them, they're not exactly lining up with where our x-coordinates actually are. We won't do both methods here, we'll just do one. So I'll just get a quick, I don't know, shout. Does anyone want to use any one particular method, whether you're adding up areas or formula sheet? If you have any preference, let me know. Okay, I'll use the formula sheet one because it's slightly faster then. So, for the formula sheet, we need our xn, we need our x0, we need our n, we need our f of values, the ones that we're doubling up, and then whatever we're finalizing up to. So these are the best and easiest place to start. N, what's n in this case? N is 4, yep, number of trapeziums. So 2 by 4 is going to give us 8. Xn and x0. So x0, we'll do that one. What's x0 in question 2? Yeah, it's going to be 4 take 0. So x0 was the 0 and xn was the 4. 4 take 0. That's obviously going to simplify. Now we need all the f of x values. So again, we're doing f of x in the order of the x coordinates that are separating those shapes. So in other words, we need f0, f1, f2, f3, f4. f0, 2, f1, 2, f2, 2f. Actually, yeah, we're doing 5 separate values. 2, f3, and then finally f4. We need each of those. Okay, that's going to come from our function here. Now, this is labeled as y, but it's f of x. f0, well, putting a 0 there is going to get you 1 over 1, so 1. f1, that's going to be a half, because it's 1 over 1 plus 1. Doubled, back to 1. f2, that's going to be a third, multiplied by 2 to get 2/3. f3, that's going to be a quarter, again multiplied by 2. 2 by a quarter gets you to a half. How far do we go? We just did 3, so finally f4, which is not doubled. f4 is going to get us 1 over 5. Again, this is just a bunch of fraction arithmetic. I hope we would all be familiar enough with how to rewrite these denominators. It'll just take some time, so I'll just cat it out to save us a bit of time for the lesson, because we've still got another half of the content to cover. 2/3, 1/2, 1/5. It's that whole inside in there would end up becoming, oops, 101 over 30. 101 over 30. You still have that half on the outside. So 101 over 60. That's pretty much it. Obviously, there's a bit more nuance to the fraction arithmetic there. I did treat that out a little bit, so the number of lines that you would do would increase a little bit more, but yeah. Any more practice of those? Happy to do a bunch of these if we need to. Cool. Okay. Just to show you the rest of the chapter, it does get a bit excessive. Like, question 3 is fine. It's now offset a little bit, so you've got to be very familiar with what your x naughts and x n's are. But then you look at stuff like question 5 and you're like, really? You're going to make me do 10 separate f values and chuck those into the formula? It's going to be a CAS thing for sure, if you decide to do it. Just judging based on the exam questions that I pulled these from, you really don't have to do any more than 4 shapes. Like this one earlier on, back in my day, was, oh geez, back in my day, was 3 shapes. This one's now 4. It's not going to get much more excessive than that. One of the other things you'll notice is that some of these questions don't appear to be the same kind of question, right? Like, yes, we've got curves and stuff like that, but where is mainly just this bit at the end? Like, what's this notation talking about? There's got some integrals in there. They've got some values associated with them. But that's what we're going to have a look at now, which is how the definite integral can be used to find the area under a curve. So this little explanation I'm about to share isn't required understanding. You don't need to know this, but it's kind of nice to just have a bit of trivia or have maybe a bit of deeper understanding of how these concepts work and why they're working the way they do. So basically, we're going to go back to thinking about it in terms of the rectangles under the shape that we're trying to optimize, or trying to, find the area of the curve under. What we find is that the more shapes that we use over the same interval, the less error there is, right? Lots of orange, less orange. If we continue to do this to its absolute limit, where you shrink them down to these very, very tiny slithers, it's going to be a very similar approach to what we did our differentiation by first principles by. We had our 2 points that had a certain width associated with it, and we shrunk that down to a very tiny thing, and we called it dx. We're going to do exactly the same thing here with our width of our rectangles. The height of each of the rectangles is exactly the same thing as f at that value, so f of x, where x is going to be the coordinate of the thing, because once again, those rectangles are directly attached to the curve. Since we're doing things in terms of incremental widths, we're going to define the area that is given by that rectangle as the incremental area provided by that rectangle. So if you imagine these as your infinitely tiny slithers, that rectangle there would have a certain dA area associated with this dx width. Area of any rectangle is length by width, so suddenly you get the formula incremental area is given by the height multiplied by the incremental width that you're evaluating over. Rearrange that, and suddenly you get a derivative type of equation. dA over dx is f of x. We also understand that whenever we anti-diff, we can essentially reverse this, right? Whenever we anti-diff a function, you go from diff to original. It's a little bit more nuanced than that. You're not going back to some original, because what we consider a derivative formula or what we consider an original formula is purely based on our own interpretation of the circumstances. There's no such thing as the original or the derivative, it's just a function. And when you're doing derivatives or integrations, you're either stepping up or stepping down on this infinite ladder, effectively. But anyway, we're going to integrate both sides. Another funny little thing, these are actually terms. dx, dA, these are actual genuine terms. And it's a bit strange to understand that these are going to cancel out, but they do. these dx's that are involved are in fact actually terms. So every time you did .dx, that's literally multiplying your integral by dx. Division of dx, multiplication of dx are going to cancel out, and any integral of a constant just gets you back to, well, any integral of d something just gets you back to whatever that constant actually is. Now this isn't really a constant, it's area in terms of x, but all that to say, when all is said and done, when you integrate your f of x, you get the area formula for that function. Big long-winded thing. I'm pretty sure I stole this from the textbook. Where do I actually take this from? I might have just had to research it myself because I'm pretty sure this stuff isn't really discussed. So again, you don't need to know the theory behind it. They talk a little bit about it here, actually. See the limit as your delta x. They use delta instead. But anyway, that's that. As for how we start using this, well, typically we don't want to do the area under the entire curve. We typically only want to do it over a certain duration. That's where we do our definite integral. So definite integral just essentially restricts the area, the interval for which we're evaluating our area. And the notation is as follows. You have some lower bound, some upper bound, and as for how you evaluate that, you do it in two steps. First is to do the antiderivative. So the same as we've done before, antiderive. Then, when you're evaluating the integral, you got your lower and upper bound. You do it in the order of upper take lower. So whatever's in the up one is your first substitution. Whatever's in the bottom spot is your second substitution. That's all it ever is, top take bottom. So what does that look like? Well, first up, we're going to anti-differentiate this. Again, you're going to use that antiderivatives table if you're not already familiar with them. You don't have to have them memorized, but you will just kind of because of having done them a billion times. They're all going to use this antiderivative here, the power function, antiderivative. Get rid of this, I keep clicking the wrong one. So power goes up, and then divide by that raised power. Power goes up, divide by that raised power. Constants get their x, and then they always have this plus c associated with them. We have our capital F of x, the antidiff. Now we're going to do capital F of top minus capital F of bottom. Top is 4, bottom is 2. F of 4 minus F of 2. These get quite long. The string of algebra that you have to do in one line gets quite big. Especially when we start looking at more application of integration, when you're doing not just area under a curve, but area bound by several curves. And suddenly you start having to do like double the length of this because you're dealing with two curves. It gets quite long. Use brackets accordingly. Even consider evaluating each of these lines separately. Like just say F4 equals this. And then on the second line, F2 equals this. And then finally do your subtraction at the end. You do lose a little bit of efficiency with it because in a decent number of cases, there's enough common terms between both of these brackets that you can actually take common factors out. And that does speed things along. But the trade-off is that you've got a shit ton of terms in the same line, and it's very easy to make mistakes doing it that way. So it's a bit of a trade-off there. But otherwise, yeah, you're literally just evaluating a subtraction here. That's basically it. And what you'll notice is that the plus c terms will end up cancelling themselves out because of that subtraction. This will always happen no matter what order you do this in. Whether you do F2 take F4 or F4 take F2, it's because they both have plus c, so it's always going to cancel out. For that reason, every time you see working out on this, they just neglect to put the plus c in there. You should still put it in the capital F when you're doing your working out, but when you're doing your actual definite integral evaluation, it's okay to leave these off. It never shows up in any of the working, even in the VCAR work solutions. So feel free to save yourself 4 characters of, of lines, each line. That's it. Any questions about that one? Cool. Okay. We're going to do this one, properties of definite integral. So kind of like how the derivative has a few properties with it, so too do the integral. There's a fair few more of them, though, because you are actually doing arithmetic here, rather than just derivative or just integration. A lot of this you can kind of get your head around by thinking about definite integrals in terms of just area components, and then just solving whatever's in the middle. We'll leave that there for now. We'll do at least 1 or 2 examples of actually just evaluating these definite integrals. And then, yeah, we should have enough time to then go through in enough detail for those examples. Okay. It's just basic anti-diff. When do we start doing? Let me find it again. A, E, and F. Cool. Where did it go backwards? We'll do one that isn't immediately obvious. So let's go with G over here. We got 1G. We're doing the integral 2 to 0 of x cubed plus 2x squared plus x plus 2 dx. I've got the question written down. On the screen share, I'll have... Yeah, I can actually have the full work solution for the other one as reference. So, with that helping you out, or otherwise, let me know. What's our first step going to be? Even if you want to answer it like a high level of just like, hey, this is what you would do. Happy to do the implementation as well.
We take the integral of the thing. So the first term, x cubed, that becomes x to the 4 over 4.
Yep. Nice.
The second term, that's going to be 2x cubed over 3.
Mm-hmm. Yep.
The third term, x, that becomes x squared over 2.
Yep.
And the last term, that's 2x.
Absolutely. Yeah.
Okay, oh yeah.
And then, yeah, plus C at the very end. Easy thing to leave off. And in this, I reckon even if you didn't put the plus C for definite integrals specifically, you probably are still fine. Because we do know ultimately that when we do our actual evaluation, it's going to disappear. So you might get away with it, but let's not tempt fate. But cool, we have our anti-diff. What are we going to do with it?
Plug in the values.
Yeah, plug in
So
the values.
2 and 0.
Exactly, yeah. 2 and then 0. So capital F2, take capital F0. Now, thankfully enough, capital F0 is just going to be 0 here. So the whole thing disappears there. So in other words, we really only need to care about doing capital F2. So that's going to be a whole lot of math. Let's do that. 1/4 to power of 4, 2/3 to power of 3, half to power of 2, plus 2, 2. And you can imagine if you were doing this by hand, and this didn't evaluate to 0, you would have to do that whole thing again. And then later on, when you have to do bound between multiple curves, you would do double that again. Okay, 2, 4, 8, 16. 16 on 4, that's 4. 2, 4, 8. 16 on 3. That just goes back to being 2. And 4. 8, 9, 10. Plus 16 on 3. 30, 46 on... Actually, this should be simplifiable. No, it's not. Yeah, 46 on 3 is it. Cool. That's it. Antidiff, sub in top and bottom, arithmetic. The only challenge is now going to be based on how complicated the antidiff is going to be, and therefore how complicated the arithmetic is going to be. Do we need to practice any more of those? Or should we move on to the next sort of little bit on definite integrals? Because that will cover how we solve things like question 4, when you don't actually know what the function is, but you can still evaluate based on some known values. Cool, let's do that. So, there's a whole bunch of properties here. The ones that are taught to you in the book are properties 1 through 4. You'll do these a bunch of times. These ones here are ones that I've added externally because even though they're not taught in the book, these have been useful in the exam. I was so mad at it because there was one multi-question that I've come across, in fact, probably twice now, actually, which you can use, like once you understand these, you can kind of come up with this yourself based on the relationship between how it's talking about area and how things dilate and shift. But it's good to just have a formula to look at instead, rather than have to evaluate it on the spot. So I've added these ones as well because they have done shit where these formulas would be really nice to know. And they've only ever been in multi-choices, so you are allowed to print this one off and put it in your bound reference. So even if it's not like, oh, it's not on my formula sheet, well, it's in your bound reference at the very least. And you're not going to do any of this in tech-free, that's for sure. So, okay, what am I doing? Basically, I have a known integral, but I don't know what f of x is. I know from 1 to 6, I get the area of 7. I know from 1 to 4, I get the area of 2. Based on my understanding of that, what would therefore be the area from 4 to 6? Literally all we're doing here is either in our minds or on picture, graphing out what those areas might look like. So from 1 to 6 being an area of 7, you might do some sort of number line thing and just say, yep, over that interval, we have a total area of 7. From 1 to 4, we have a total area of 2. Sweet. So if we're doing 4 to 6, what's that going to be? Well, if my total is 7 and this part is worth 2, the remaining part is worth 5. That's all this says. You can take any interval from A to C and split that up into as many little bits as you want. So the interval A would be 1, concluding at C for 6. You can split this up into any number of integrals that you want, so long as you do the integral for each of those in the middle. That's what the property says. As for the algebra and geometry of it, this is what you're effectively doing. Slicing up the area. Fair enough on that one? Cool. Next up, again, we know the integral of an unknown function. We want to evaluate a slightly different integral. Has the same boundaries, but this one's got a coefficient of 4 in there. This one we kind of know already and we have a lot of practice with in all sorts of places, but most recently derivatives and actually antidiff. They both have the same property, which is any constant coefficient can be taken out of an integral. So rather than having the 4 inside this integral, the 4 can be outside the integral. Suddenly, this looks exactly like this. So since they're the same thing, we just replace one with the other. The integral is 7, and we're just doing 4 times that integral. Next up, we have, again, 2 known integrals over the same domain. Here is a separate integral, same domain once again. It's going to be the addition of those 2 functions, though. Even though we don't know what those functions are, we do know the individual components of them. And because integrals can be split not just across little area sections, but also across the functions that are included in them, f plus g is the same as f integral plus g's integral. You just split it up. So instead of doing f plus g in the same one, you split it up across the two. This one we know, this one we know, so therefore we now know this one. We do this a bunch. We technically did that right now when we did our last example. When you're evaluating the derivative or the integral, you do them one by one, not all at once. Lastly is one that I haven't quite discussed yet, which is if you reverse the order of the terminals, so instead of having A on the bottom and B on the top, the other way around, it's the same as getting the negative of whatever the original integral was. Literally, all we're doing is flipping the order of the subtraction. That's it. That's why it comes out to be negative of whatever this was. If we look back at the handwritten section that we just did, we did capital F of 2 minus capital F of 0. That would come out to be 46 on 3. If we swap that order to be F0 minus F2, we would now have 0 minus 46 on 3. It now becomes a negative version of itself. That's all this is saying. Swapping the order of the terminals is the same thing as just making the original integral negative. So when we apply it to this sort of circumstance, again, we can see the terminals are kind of similar, but they're just swapped. That's our mental note to be like, okay, terminals are swapped, so that means that whatever this one is the negative of. But it's not quite that simple, because this one actually isn't exactly the same. There's also this plus x involved in there as well. So we're going to actually use two properties here. The first is to split it up. There's a plus between these two functions, so we can split them up accordingly. Now we can use that whole, over here. Now we can use that whole equivalence here, where flipping the terminals just makes it the negative. So rather than this being positive a, it's now negative a. Finally, this one is just a solvable integral. It's just the integral of x. So we antidiff it to x squared, and we do our capital F of top minus our capital F of bottom. Put them all together, and we're happy. So this is the kind of thing you'll get in like the SACA exam. Won't be any one of these things, it'll be multiple back to back. Cool with that?
I was wondering, is it common to get these questions where we're finding it in terms of A? Is that common?
Yeah. Yeah.
Okay.
It's not here, it's in the exam. It happens quite a bit. In fact, I probably pulled some of these from the exams, to be honest. But yeah, getting them in terms of other coefficients, it's the same thing either way. Okay, I do have other examples with the ones that I've added myself. They are already there. They're not going to be relevant for this lesson. As long as you know how to read this, identifying, okay, I have A, B, C, that means I'm going to put the same A, B, and C on this side. As long as you understand how to read those, that should be enough. We'll do a practice of some of the stuff in here first. Once we're comfortable with that, if we still have time, we'll go on with the other ones. Because again, they are kind of niche. They've only come up like 1 or 2 times across the entire history of methods. So let's crack on with the more common ones. Starting with, let's go with, but they're also similar. Let's go 4b. Integral 4 to 0, h of x plus 3, with the knowledge that integral 4 to 0, h of x regularly is 5. That's our known. This is our unknown. I'll pull up all the properties if you want to look at those on the screen share. We'll also get a screen grab of it too. All right, how are we going to evaluate that top green integral?
Chris, could you resend the screen grab? It's just not working for me.
Interesting. I'll do that again.
Okay, I can see it now. Thanks.
Easy. So probably just look at the top four there. Will be the only ones that are valid. You can even just go them in order, right? Like, can we use the top one? Well, the top one says that we can evaluate definite integrals in individual sections. We don't really have multiple integrals in the sequence, at least not yet, because the what we see from example 1 or property 1 is that it's the terminals that are changing in that example. Terminals aren't really changing here, so probably not relevant. Dot point 2, terminals are the same, cool, but what's being done there is taking out
Can
coefficients.
you use the third one?
Say again?
Can you use the third one?
The third one, absolutely. We got a plus or a minus between two little bits inside of the function, inside of the integral, so we can split them up. Integral 4 to 0 h of x plus integral 4 to 0 3. I'm being a little bit lazy with those dx's. Make sure you include those when you're doing your actual working out. Now from here, things should be a little bit easier. One of those we know immediately, the other we can solve. 4 to 0 h of x, 4 to 0 h of x. So that one is 5. All that's left to do is this one here, which is just this previous example here, but a lot easier to antidiff. So I'll just quickly go through that one. Antidiff of that gets you to 3x. You can put your plus c in there. Capital F of 4 minus capital F of 0 is that one. So 4 3s are 12, and then the other one's 0, so it's just 0. 5 and 12. Final answer would be 17 for that one there. As far as what you might get in the exam, if you have a look at the screen share in the background, I was pulling another one up. Here's that whole thing of getting the C's and D's and other actual coefficients in there. Yeah, we can probably do one more example if you guys want to stick around for it, because this will give you an idea of the level of complexity you'll need for the actual exam. So if you're going to stick around, that's awesome. If not, I'll let you enjoy the rest of your day. But okay, so we got 3 to 10, which is equal to C. We got 7 to 10, which is equal to D. We want to find 7 to 3. So there's a couple of things going on. The ones that we know have different domains associated with them. The one that we're trying to find also has a different domain associated with it. So we got to start thinking about what kind of properties would be involved there. I'll start writing those out while you guys have a peek at the cheat sheet of
Wait, Chris, is this from the final exam?
2023. Yeah, 2023 exam
Okay,
2.
cool. Wait, what's the current study design? Like, what years is it from?
Question. 2024.
Okay.
2024 is current study design. These are
Yeah.
in the current study design.
Yeah.
Just for reference, the things that are different in this study design are pseudocode, bisection method, Newton's method. Is that it? Trapezium thing that we just looked at.
Yeah.
I think that's it.
But other than that, is it basically the same?
Yeah,
Okay.
yeah. The only thing that you'll be coming across before would be like matrices stuff, in the previous study design, you're not going to touch matrices. You're going to look at it and know immediately, oh shit, definitely not going to do that.
Okay.
Everything else is going to be totally valid for sure. But cool. Okay, so let me start writing those out. Integral 10(3) of function is equal to c. Integral 7 to 10 of function is d. Integral 3 to 7 of function is something. Cool. So what I'm noticing is 10 to 3 and 10 to 7. Oh, maybe before I say that, does anyone have any ideas they want to start us off with? Cool. So what I was going to say there, 10 to 3 and 10 to 7 are kind of just subsets of the same domain. So if you think about little number line, 3, 7, 10, if from 3 all the way to 10 is going to be C, then 7 all the way to 10 is going to be D. What we notice is this remaining bit here, 3, 7, matches with this. But it's not quite right, because if we were to do the exact same notation, we would need integral 3, 7, not 7, 3, like that. So, if we know that C is the total bit here, D is the little bit in here, whatever's left over, you got C subtracted from D. That's this bit here. But because these terminals are flipped, oh yeah, sorry, I didn't notice you had your hand up.
Since it's in reverse, will it be negative?
Yeah, that's exactly right.
So D minus C.
That's it. Yeah, you chuck a negative at the front, which is going to flip it to D minus C. That's going to be the answer. Smashed it. Yeah. So again, what you can see here is that you have to use basically two properties here, which is property 1 and property 4. 1 and 4 there. I don't know where the other weird one was. I'm not going to do two of the same question in the same exam, and we don't quite have time for it. But if you want, feel free. I've got all the exam solutions and stuff written out in the classroom tab. Feel free to have a browse through the multi-choice sections of 2023 and before. You'll probably find the weird ones that need the .5 and .6. In fact, I might have copied them directly into here, actually. Or maybe I made up my own. One of the two. Anyway, they'll be in there. But they're definitely harder if you don't know these. That's for sure. Cool. All right.
I think I had a question similar to this in the 1-2 exam.
Yeah. Yeah, these are similar in 1-2, I think. Because you do learn definite integrals in 1 and 2, so it makes sense that they would show up. Yeah.
Yeah, I wasn't able to do that question.
Yeah, by far, because basically all of these examples 1 to 4, the properties 1 to 4, pretty much all of those can be graphically shown, like we just did here with a little picture. So that little, like, you noticed I didn't label any of the examples with like the mathematical property of it. I just drew areas and said, yep, cool. If that's a C and that's a D, then that's got to be C minus D. You know, drawing little geometrical versions of these things. It's a nice little visual way of doing things. So, yeah, if you remember where those were, oddly, if you can, feel free to go back on those and see if you can smash them out. That'd be cool. But otherwise, you got some pretty basic ones in question 4 here, and maybe in the the chapter review, you'll have, where was it? Bang, bang. Yeah, here we go. Here's some ones. See how they got the different domains, and yeah, these will be nice ones to go along with. Anyway, that's about it. I'll leave you guys to enjoy the rest of your day.
Hey, thanks.
Thanks.
Have a good day.
You too, mate.